So as we get to winding up chapter 6, we have 6.3b, and then we just have 6.4 to do. We're going to finish this up with a focus on the antiderivative. All of the antiderivatives are easily integrable. They're recognizable. Like, we're not getting into U substitution yet. We're not getting integration by parts. That's all chapter 7. Okay, this is just like, you know, integrate easy functions, like that are recognizable as they have a perfect antiderivative. So just to summarize, by the end of this lesson, you'll have 3 ways to evaluate an integral. So we have seen the first way is geometry. Okay, geometrically. The second way is with technology. Okay, where the function is not a geometric shape and does not have an analytical antiderivative. And so now we're finally to step 3, which is analytically. And analytically means we're using the antiderivative. So just some notation that you're probably familiar with, but we'll review anyway. F prime of x is our derivative notation, thanks to Mr. Newton. F of x is the original function. And so then f capital plus our friend, the constant, plus c is the antiderivative. Now, why do we need the plus c? Okay, the derivative of c is 0. And so you don't know what that constant could have been. It just disappeared. If you're looking at the derivative, there could have been a constant there. So we have to account for that constant by including the plus c each time. Okay, and then the definition of the integral. Any integral over the interval a to b of f of x dx, we went through the development of that. The result of that is capital F of x plus the constant c, and then we note that with changing the integral to a bracket from a to b. Now it's acceptable to just put one bracket. When you move on to college and use a different textbook, or you might have a professor that's really old school and she has been around for a long time, you may see double brackets like that. You may also see just lines like this. But that tends to be kind of out of favor because it also could look like what? Okay, right. And you know, the brackets, if you do double bracket, then that could look like a step function. So that's why I tend to just do this one, because it's not a step function and it's not an absolute value. It's pretty clear. And then we evaluate by plugging in those bounds. And which bound gets plugged in first? So that would be f of b plus c minus f of a plus c. And eventually what happens to the 2 plus c's? Right. And so we are left with just f of b minus f of a. And so that's just the definition. Got it all in one place there of the antiderivative. So we'll spend the rest of the time just doing some problems and working through our antiderivative. Some of the antiderivatives you recognize, like the trig ones. You should, if you know your derivatives, you should know your antiderivatives. For polynomials, we'll go through what the rule is for how to do a polynomial factor. Let's start with that. So let's start with the polynomial that is the integral from -1 to 2 of the function 10x to the 4th minus 6x squared plus 3 dx. So this is just a simple polynomial. With polynomials, the antiderivative needs to be 1 power higher than what it was. So the rule is instead of being 10x to the 4th, it's 10x to the 5th, but you have to divide by the value of the new power. And then minus, instead of 6x squared, it'll be 6x cubed. Again, divided by the value of the new power. And then 3, the constant, becomes 3x. And then the constant c plus added up to the end. And then we're going from -1 to 2. So overall, we're looking at 2x to the 5th minus 2x to the 3rd plus 3x plus c. Evaluate on the bounds 1 to 2, -1 to 2. And then it comes to the point where you now evaluate. So this should be review. We'll take the 2 as our upper bound and plug it in. So 2 times 2 to the 5th minus 2 times 2 to the 3rd plus 3 times 2 plus c minus 2 times -1 to the 5th plus 2 times -1 cubed minus 3 times -1 minus c. And so we show our c's cancel each other out. And we're left with 64 minus 16 plus 6 plus 2 minus 2 plus 3.
We don't have to show C all time, we can just show it once.
Right. All right, so plus 2 minus 2. And 64 and 6 is 70, minus 6 is 54, plus 57. Yeah, I think 57. Okay. Okay, any questions on that one? All right, that was polynomial. We're going to try and do one of each with you. Okay, the next one I want to do with you is the integral from 4 to 7 of the function 1 over 2x minus 1 dx. Okay. If the first one was a polynomial, do you recognize what a 1 over function might be? Okay, there are a couple things that could be 1 over. Okay, 1 overs could be natural logs. They could also be any of our inverse functions. Inverse sine, inverse sine, inverse tangent, inverse secant. So this one, because the power is 1, is going to be the logarithm. All right, when you do a logarithm, a couple things you have to remember. It's the logarithm of the absolute value. Okay? The definition of a logarithm has to maintain that logs are always greater than the interior of a log has to have a positive domain. And so the absolute value of 2x minus 1. But we have to divide by something also. Okay, you've got to divide by 2 because that is the anti-chain rule. And then plus c from 4 to 7. Okay, so with the chain rule, when we take derivatives, we have to multiply by the interior. When we do an antiderivative, you've got to do the anti-chain rule also. You've got to divide. We'll be proving that more with the u substitution later. But, all right, once we've got that, so we've got 1/2 of the natural log of 14 minus 1 plus c minus 1/2 of the natural log of the absolute value of 8 minus 1 minus c. So cleaning that up, one-half of the natural log of the absolute value, I don't need the absolute value anymore because these are positive, of 13 minus 1/2 of the natural log of 7. And our rules for natural logs say that the subtraction of two natural logs can combine them into a single natural log with what in the inside? The fraction, right? 13 over 7. And what can you do with the half? You could write it as the natural log of 13 over 7 to the half, which you could also write as the natural log of the square root of 13 over 7. Okay, none of those is better or worse than the other. We're just looking for, what are you looking for in a multiple choice answer? I'd probably, me personally, probably stick with the first one, but there's not anything horribly wrong with doing it a different way. Okay. I love how you switch back and forth all the time. Okay, how about another 1 over? But the integral from 2 to 2 over square root 3 of negative 1 over the absolute value of x times the square root of x squared minus 1. Okay, so like I said, I promise you all of these will be recognizable. Okay, it should be, oh, that is the form of the derivative of something that I memorized at one point way back when, and so hopefully you can go backwards and figure out the antiderivative of that. Okay, so this is one of our inverse trig ones, and it's one of the co-inverse trig ones, like it's either inverse cosine, inverse cotangent, or inverse cosecant. How do I know? It's negative, because it's negative. That's how I know it's one of the co's. All right, so which one is this? Okay, so this is the inverse cosecant of just plain x. Evaluated from 2 to 2 over rad 3. So the inverse cosecant, 2 over rad 3, minus the inverse cosecant of 2. I did my plus c minus c already. I'm not a big fan of inverse cosecant. I'd much rather work with inverse sine. So I can change each of them to their reciprocal. I just have to change the interior to its reciprocal also. So I'm more of a fan of working with inverse sine and cosine than I am of inverse secant, cosecant. So now I can use my unit circle. And I want to know when on the unit circle is the primary time that the sine achieves a value of rad 3 over 2. That's going to happen where? Okay, pi thirds. And then minus pi sixths, which is equal to pi sixths. Okay, how you doing? Okay? Okay, a couple more. Let's do a trig one. The trig are going to all be recognizable. You won't need integration by parts. You won't need the Lippitt test. You won't need any of that. Okay, till later. So let's just do a basic one. Let's go from pi fourths to pi halves, and let's just do the sine of 2x dx. We all know the derivative of sine is cosine, but what's the antiderivative of sine? Negative cosine. So I need negative cosine of 2x, but I also need the anti-chain rule. Okay, so divide by 2, and then plus c, going from pi fourths to pi halves. Doesn't this just feel like you've met an old friend again? Okay, it's like a little reunion. All right, we're coming back. So I'm going to just rewrite this. I'll put negative 1/2 out in front, and I want the cosine of 2 times pi over 2 plus c plus 1/2 of the cosine of 2 times pi fourths minus c. All right, let's take care of our c's, and we'll clean up our cosines. So we have negative 1/2 cosine of pi plus 1/2 cosine of pi halves? So it's negative 1/2. What is the cosine of pi? Negative 1 plus, and what's the cosine of pi halves? 0. So I'm just looking at positive 1/2. One more. Okay, so we have seen a polynomial, a logarithm, an inverse trig, a regular trig. Can you think of anything that's left? Say it again. Circles we're going to do with geometry. Exponentials. So something like, yeah, because we've done logs. We just haven't done exponentials. All right, so that's the last one. All right, last one. You should fit it. It's only 5.
We usually have like 2.
All right, 1 to 4 of 5 to the 3x dx. So this is an exponential. So let's review how to take the derivative. Actually, I'll do that in a different color. So the derivative is a to the b times b times the natural log of a. Right? That's the derivative. You take the regular exponential, multiply it by, b prime, okay, and then the natural log of a. Okay, so the antiderivative is going to be a to the b divided by b prime and the natural log of a. So in this case, we're going to have 5 to the 3x divided by 3 and divided by the natural log of 5. Plus c, going from 1 to 4. So that'll be 5 to the 12th over 3 ln 5 minus 5 to the 3rd over 3 ln 5. There's not a, I don't know if there's a whole lot of practical use in simplifying that. Suppose we could take out 1 over 3 ln 5 and leave me with 5 to the 12th minus 5 to the 3rd. 5 to the 12th minus 5 to the 3rd is not 5 to the 9th. Okay, you can't subtract powers. Only can subtract powers when you're dividing things, not when you're subtracting. So I don't know if there's a whole lot of, maybe you could take out a 5 to the 3rd. So 5 to the 3rd over 3 ln 5. That would leave me with 5 to the 9th minus 1. I don't think that's any better. All right, so I would just probably leave it in the first form. Yeah. All right, so we have seen polynomials, trigs, inverse trigs, logs, and exponentials. Everything should be recognizable in a form that you should be able to take its antiderivative for.